have set 17 goals regarding sustainability. And the goal number 6 is water, access to clean water and sanitation for all. But sustainability also means that we need to plan ahead of time as the future brings new problems. Sadly, 129 countries are not on track to comply with the goal set for 2030 for sustainably managed water resources. But how did we get in this situation? Isn't Earth the blue planet? If we take a closer look, if we take all the water on our planet and make a sphere out of it, it isn't as large as many of us may have thought. The spheres representing the non-saline water are even smaller, as you can see. Fresh water takes up just 2.5% of the total water on our planet, and a big part of it is in the form of ice. Only 0.3% of the total water on our planet is exploitable. Besides that, we also need to consider other factors, like uneven distribution of space in the spatial and temporal parameters. A great example of that is my country, Greece, which is divided by a large mountain range called Pindos in two. The western side gets much more precipitation due to the humid winds coming from the Ionian Sea and being stopped by the mountain range. But the eastern side has much smaller heights of precipitation. The eastern side, though, has some of the biggest urban areas like Athens and Thessaloniki, some of the most important areas regarding agriculture, and some of the most famous tourism destinations. All those activities demand more water in the summer months, when precipitation is lowest. The same can be said on a larger scale, as you can see on the map on the right. As you can see, countries around the Mediterranean face problems regarding water stress. In this table, we can see that many countries around the Mediterranean get a big portion of their water needs covered by using groundwater resources. Some even use more than 40% of their of their water needs from groundwater resources. What exactly are groundwater resources? An aquifer is a structure where the pores of rocks or sediments are saturated with water. Large quantities of water can move through an aquifer, and the movement of water depends on the hydraulic slope and the other factors like hydraulic conductivity. Aquifers can be confined. When this happens when a confining bed over and under the aquifer block water from moving in the vertical direction. And they can also be unconfined, in which case the water table represents the top of the zone which is saturated. Aquifers get recharged by rainwater. Precipitation in general, I should better say. Aquifers can also get contaminated, and sadly, because of the phenomenon of the depression cone around pumping wells, contamination many times gets withdrawn from pumping wells. And this water is needed because it is used for agricultural consumption and other purposes. So the goal of my thesis was to identify the pollution source in a given area so that the polluter pays principle can be applied, and later remediation methods can be applied to stop the pollution from spreading further. It is a part of a greater project which was initiated by my supervisor, Mr. Kontos, where machine and deep learning methods were implemented to identify the pollution source in a given area and also pseudo-optimize the monitoring network. In the first part of this larger project, the particle tracking method was used, but in my thesis, we used the Modflow simulation program, which more about that later. So we created the theoretical study area. Some of the parameters of the area can be seen on the right. The area was simulated for 2,500 days in a steady state flow field. The grid contained 29 rows and 29 columns, giving us 841 cells. And each scenario had 6 pollution sources. Each scenario has a color representing the pollution sources on the map you can see on the left. In my thesis, only one scenario was used, and in the wider project, we had 4 main scenarios and one scenario that combined all the pollution sources of the previous 4. So we had 6 pollution sources per scenario, 21 different values of hydraulic slope, and 11 pumping rate values for each of the 2 pumping wells on the south of the map, giving us a total of 15,246 number of simulations needed per each scenario. As I mentioned previously, Modflow was used. It is a simulation software of the United States Geological Survey that is widely recognized in the field. It uses finite differences and uses the well-established equations of advection and dispersion for the pollution flow, and the combination of the Darcy and continuity equation to calculate the hydraulic flow. Another software called the Model News was used as it provided the friendly interface for the user and thus gave the opportunity to check the results. The results can be shown in those ways. But we needed to automate the process, which made us use another software called FlowPy. FlowPy is a Python library, Python, the well-known programming language. It is also created by the United States Geological Survey, and FlowPy uses Modflow through Python commands. It can interact with other Python libraries like NumPy, Matplotlib, etc., and can automate the process of giving input to Modflow and then saving the results of each simulation of each dataset, and then continuing forward automatically. I'll show you some parts of the code we wrote to simulate our problem. As with every code, in the beginning, you import the libraries that you'll need to use later. Then we provided the Python the coordinates of the potential pollution sources of each scenario, and then we created a function which created the groundwater flow field and the groundwater transport problem. I can give you all the details because it would be just too much information to present in a slide. Then we created a function that automated the process. It read a file you can see on the right. Each of these numbers corresponds to one pollution source. For example, 1 is the first pollution source, a slope, a hydraulic slope, 0.0 means 0 hydraulic slope, and the other 2 numbers correspond to each pumping well. Each of them in the first example abstracted 2015 and 2025 liters per second. Then we had some parts that made the code user friendly, so we could run just some data sets that we needed to check and make the simulation process more easily organized. And now I'll show you how the results of each simulation can be portrayed. This is the result. Those are the results of one simulation for 2,500 days. As you can see, the pollution starts from a cell, which is the pollution source, and then moves towards the two pumping wells, which are the two green dots on the south of the map. Then the results had to be saved in two different file types. The first type is an Excel file, basically, which in each line contains results for every cell of the grid. So we can understand which cells were polluted, when was the first day each cell was polluted, etc. The type B results give us TXT file, which has every number corresponds to the pollution in a given cell in a given day. So the name of each file corresponds to the day of that the results represent, and the position represents the pollution concentration in that cell. Then we applied machine learning methods using an application called WECA, which helps to make the machine learning process easier for the user. Basically, you don't have to write all the code. I won't stay too much on that. Machine learning used feature selection. Thus, it removed the cells that were least important to find the pollution source. Two algorithms were implemented, random forest and multi-layer perceptron. And in the end, we got 6 different solution combinations. RFFL, for example, means the random forest algorithm with a subset of feature selection. And there you can see the results of the implementation of the machine learning methods. By implementing them, we reduced the number of wells, of monitoring wells needed to find the pollution source. With just 16 wells, we got great accuracy of 100% using the random forest algorithm, and the multi-layer perceptron didn't have such great results. Then we implemented the deep learning methods to also temporarily optimize the network. We had many subsets that each featured different frequencies of sampling. We had 9 sampling frequencies each day, every 10 days, every 20 days, etc., up to 80 days, and 3 subsets that led to a total of 27 combinations. The results are presented in this table, which provides us with an alternative option. We can use a network that has 53 monitoring wells, but uses a sampling frequency of 50 days, which is much longer than the solution mentioned previously, which had to force a sampling frequency of every day. There you can see the citations of this presentation. That's it for me. Thank you for this presentation.
So thank you so much, Marios, for this nice presentation. Alors, perhaps there is some question in the